Hey there, Engineering Academy. It's good to see you all again, although I'm not really. I just wanted to say great job on getting the assignment in last week. And this is going to be our next video. This is labeled Discussion Board Week 2A, and there will be another one as well a couple of days from now. You may want to go back and read the comments and the answers that went out in that assignment. Don't forget you have the ability to go into Classroom and look at what everyone else wrote as well. So I do encourage you to do that. You don't need to have any class comments though, only put them into the submit area. But if you want to refer to what someone else said, as Nolan did at one point, that is great. It is a discussion board. It should be vibrant and have some good back and forth. And I'll be transferring the grades across into RenWeb pretty soon, so you'll see that. Now, just want to update you all on who actually is in this class right now, because one of the exciting things is that we can be all together, grades 9 to 12. So I think it's probably mostly settled out at this point. Here is who we have in the order that Google Classroom is showing. We have Eliada Mordine, Abby Fiku, Joshua Frankenfield, Cassie Ginto, Isaiah Jones, Sam Krautman, Hunter Labrie, James Lowen, Alan Lopez, Nolan Lundgaard, Angel Madrigal, Zach McNeese, Davis Peterson, Caitlin Tang, Pedro Torres Leva, and Teleos Someno. It's just great to have all of you. I'm so excited for this group of 16 and looking forward to really good things this year. Now, a couple of sort of housekeeping things before I really get into the content for today. Most videos are going to be pretty simple, like the previous one and like this one, but I will also try using, as of today, a whiteboard app. I think that'll be clearer than me using a physical whiteboard. So you'll see that today, and let me know if you think it's not working and I can try something else too. The reading today in your Statics for Dummies is probably the longest, it's the longest one that I have planned for the next couple of months. So if it feels a little lengthy, that's because it is. It's 11 pages, and that means this video is going to be just a touch longer than usual as well. I'll try to generally keep it to about half an hour. We are going to go over a whole bunch of mathematical principles. We want to make you the very best mathematicians in this school. That is my goal. And for the most part, it's going to be things that you have encountered as early as middle school. That's why I feel comfortable delivering it to grades 9 through 12 right here in the first week of school. But it's also going to be true that the freshmen will have the most challenge with this. And that again is the reason why the assignments are different. There's going to be a basic review assignment and then an advanced math review assignment. So make sure that you pick the right one. If you're in 9th or 10th grade, you must do the basic one. If you're in 11th or 12th grade, you must do the advanced one. And I'm just thinking now as I speak, what if somebody from the younger grades wants to do the advanced one? You know, I guess I wouldn't mind, but I would have to grade you on that basis. So let's say basic for now. You can write to me if you think you do. Basic for 9th and 10th, advanced for 11th to 12th. Now, I really want you, if you are not doing this already, you should have some kind of a pen, stylus, something, and be taking notes. As you are doing the reading in the textbook and as you're listening to me, you should be taking notes. It's all going to connect. You may want to maybe even like have 2 columns. Maybe you have like a column that has notes from the textbook, and then maybe you have like a parallel column where you supplement it with things that I'm talking about. They're going to be pretty closely matched today and in general, I would say. Now, my preference is that you do take notes on paper. I think that is better for you, better for your mind. If you do choose to use some kind of digital medium, then it really has to be a handwriting style app. It can't be typing into a doc because you won't be able to show diagrams and do math working and all of that. It just won't work. So that's why I say the paper is the easiest thing. We don't have to worry about the technology side of it. Technology can get distracting. I am using the digital whiteboard because that's the best way for me to deliver it to you. But for my own note taking, I use paper. If you are going to use a handwriting kind of app, please don't delete your working. That's one of the reasons why I don't like it, is like someone makes a mistake and then they'll select the mistake they made, they'll drag it to the right place, or they'll just flat out delete it and write it all again. I want to see the process. I want to see the working. And that's why I say sometimes the digital tools are actually worse. They don't preserve that because we don't like that. We like to go back in history and change it to be correct. So I understand that, but yeah, those are my preferences. And before I get into the content, last thing is I want to just say a little more clearly just what statics is all about. We're spending so much of this year studying statics. It's going to take us right through to January. And it's a foundational branch of physics and engineering. And I want to make sure that we all understand just what it is and what it isn't. You kind of got that from the first reading, the first session, but just in case, let me go over that again. So statics is when we have a situation where the forces are balanced, okay? Taking notes, so it's when the sum of the forces are balanced. It doesn't mean there is no force. It doesn't mean like F equals 0, where F stands for force and 0 is standing for nada. It is sum of all forces equals 0. So right now, this Jenga tower is, first of all, very short. Wouldn't be a terribly exciting game, but there's not an absence of force here, but this is a statics situation. It's not that there's an absence of force. There are forces all over, all through, all around this thing. Just to name a few, each individual brick, each individual block has a gravity force that is pulling it straight down toward the center of the Earth. Each of these little bricks, if you know anything about gravity, are also being attracted towards me and towards every other object in this room, because that's how gravity works. Gravity is always pulling every object in the universe towards every other object. There are no exceptions to that rule, as far as we know. There is air pressure pressing on all sides of all of these blocks, and that creates real force. This block is touching this block, so there is a contact force. The table is touching these bottom blocks. So again, that is a contact force, and those things are all happening right now. But the really cool thing is that even though there are thousands, millions, kind of depends how you would break it down to what level of granularity, but there's so many forces, let's say, so many forces happening, and they all perfectly balance out to 0. Okay, and the reason I know that is very simple. This tower is not accelerating. It's just staying there. And when there's no acceleration, there is no force. No sum force, no net force, no total force. Those are all the ways that we can say that. And so, yeah, that's why we can call this a statics situation. Now, we won't always stick to statics in our engineering. We will also do dynamics, of course. And dynamics is when it gets a little more interesting. And that's when things do start to fall over. All right, let's go into the working. And once again, make sure you're taking those notes. Here we go. Okay, the first section in there is to do with significant figures and decimal places. And the book explains it pretty well, but I know this is a potentially confusing topic. So, oh, you know what I'm going to do? I'm sorry. I am actually going to lay my screen flat so that camera will go black. I am still here. Okay, so significant figures versus decimal places. So when you have a number, you know, like 3.1415, right now, this has 4 decimal places, and that's kind of easy to spot. But if we talk about significant figures, or sig figs, as Mr. Hurt will often call them, we're talking about the number of figures that give you a sense of the precision of this number. And we actually have 5 significant figures, okay? The 3 counts as a significant figure. Now, here's another example. If I had the number 3,000, The number 3000 is only one significant figure, okay? This is one significant figure. Those 3 zeros on the end there actually don't count. They are not significant figures. When someone tells you 3,000, whatever it might be, 3,000 pounds, what they're really saying is that it could be a little more, could be a little less. Maybe it's 2,900 pounds. Maybe it's 3,261 pounds. But since they only gave it to you in one significant figure, that's all that really matters for this analysis. Let me give a little example here. Think about a block of wood. Someone cuts a block of wood. Look at that. That was messing with my block of wood right there. And this block of wood, they hand to you and they say this thing is 25 centimeters long. Now, when someone cuts a block of wood and says, here, this block's 25 centimeters long, what they actually mean, if we're going to be strict about it, this thing could be as long as as short as 24.5 centimeters. It could be as long as, maybe say 25.49 centimeters. If it were any lower than that or any higher than that, we wouldn't call it 25, but it could be anywhere in that range. And we could still call it 25 centimeters if we're only using those two significant figures, which we did. The 2 and the 5 are the two significant figures. So take this block, and then we're gonna cut this thing up. Okay, we go at it, and we get a little drop saw or something, and let's say that we could cut it into 8 pieces, and we can somehow guarantee that those 8 pieces are exactly precisely 1/8 of the original, whatever it was. Nominally, we're calling it 25 centimeters. Now, if you take the number 25 and you divide that by 8, the answer you get is exactly 3.125 in the math world, okay, mathematically. But what if the original piece had actually been that 24.5 centimeters? We still would have been right to call it 25 because we're only using 2 significant figures. But if you take 24.5 and if you divide that by 8, what you actually get is 3.0625. If it had been let's say 25.4, if you divide that by 8, that is actually 3.175 centimeters. Sorry, I should put units all the time, always. You can see that while this one is kind of the true mathematical answer, the actual physical objects could be anywhere between 3.0625 centimeters and 3.175 centimeters. That's actually kind of a big range of values. Okay. Now, if you report those to 1 decimal place, that is 3.1 or 3.2, which there's still a discrepancy. There's still a range there. You still can't say with confidence whether it's 3.1 or 3.2 or anything in between there. If you go down to if you go to no decimal places, then the answers are in agreement. Both of those numbers would round off to be 3 centimeters. So that's a little bit of an illustration. When you go back to the original problem right here, it was 25 divided by 8. Now, the number that had the least number of significant figures in that question was the 8. Okay, the 8 was the lowest number of sig figs. It only had 1. The 25 had 2, the 8 had 1. And so the rule that was described in the textbook is that you're always governed by whichever number had the least number of sig figs. In this case, the 8. It had 1. That's why the only answer that we can really trust is the 3 centimeter answer at the end. 1 significant figure, because the original information only had one significant figure, you can really only give an answer with one significant figure. Okay, that's how it works with multiplication and division. Now, it really takes courage. When I ask you what's 25 centimeters of wood split into 8 equal parts, it takes a lot of courage to not say this 3.125 number, because mathematically that would be the right thing to say. But in engineering, it's perfectly fine. In chemistry, it's perfectly fine. In physics, it's fine to say, no, the answer is 3. And no teacher who's talking sig figs is going to look at you strangely. It's just not what we do. It's fine to keep that sig fig rule. Now, one very important thing I will say as I close this little section and move on to the next is that we don't ever want to cut those off before all the working is done. Like, you might be multiplying, adding, subtracting, squaring numbers. There might be a formula. Here's a formula we're actually going to use later. We're going to say I equals BH cubed on 12. And you have to input the B, you have to input the H, you got to cube it, you got to divide by 12. And you don't want to like cut down to those sig fig rules in the middle of the process. You want to wait till you get your answer for I, for capital I right there on the left-hand side. And only at the end of doing all the math do you apply the sig fig rule, okay? That is that. If that didn't make a lot of sense, reread the textbook section, rewatch this portion of the video, write a question in the discussion board. That's why we're doing it recorded. You can slow things down, you can go back, you can look at it all over again. I myself have some questions about significant figures for Mr. Hurt, and I'm going to be asking him those this week. All right, going right along. Let's talk scientific notation. Scientific notation is simply a way to easily write numbers that are either very large or very small without having a whole lot of zeros all over the page. And this does happen a lot. You might be designing the Sydney Harbour Bridge. You probably wouldn't be designing the Sydney Harbour Bridge because it's already designed. But let's say you had a bridge and that bridge just had massive, massive forces going on. 13,400,000 newtons of force in one of its members. Or maybe you're doing theoretical physics and you've got these super tiny, I'm sorry, I didn't want to do that one, do kilograms. You have super tiny masses because of the little atomic particles you're working with, okay? These will be the sorts of scales that you'll have with big decimals, with lots of zero places, or big numbers with lots of zero places for like in the millions or the trillions. So what we do, the rule is simply this. You can only ever have one number right here in front of the decimal. Okay, for this one, it would be 9.0. You can only have that one number. Then you have as many decimal places as you want. It depends on how precise you're wanting to be. In this case, I'll just keep exactly what was already there. In the first example, by the way, I have how many significant figures? Your answer should be, say it out loud, 3. For the second number here, the one in kilograms, how many significant figures are there? You have 1, just that 9, okay? Remember, zeros before or after don't count. That's what the textbook said. Now, sorry, to come back to it, we write that number with the one number in front of the decimal, and then you always have times, and then it's always times 10, then it's times 10 to a certain power, okay? We're always going to put some power right here. I'll do it over here as well. And the question is always, what power are we putting the number to? And really, you're just kind of like jumping along the decimal place. We're saying, how many spaces would this decimal, this one right here, how many spaces did that have to jump from what it should be back here originally to what it is right now? And the answer is, if we sort of started here, we would have gone 1, 2, 3, 4, 5, 6, 7. So it gets a little number 7. And for those who aren't used to my handwriting, I do cross my 7s to make them make it very obvious that they are not number 1s. I picked that habit up in Haiti because in Haiti, when you write a number 1 in like French style, it actually looks like this. And that can look a lot like a 7. That's why we do it. Bye-bye. Okay, back over here for this second number in kilograms. Again, we say, how many places do we have to jump it? Well, we would go 1, 2, 3, 4, 5, 6, and it's -6 because we jumped the other way. We jumped this way, whereas back over here, we jumped that way. Or maybe you want to think of it the other way around. Maybe you want to think of this original number's decimal jumping to go this. But either way, I think it's clear that you're going backwards. When you have negative exponents, you get teeny, teeny, tiny numbers. When you have positive exponents, you get big, great big numbers. Okay. Now, it'd be good practice for you actually to try this out for yourself. Like, what if you took those two numbers that I have on the screen, and what if you multiply them? What would you get? Let me do it right here. I have a little on-screen calculator, which you guys can't see, but I'm going to do it. Maybe you want to pause the video and do this yourself as well. 13,400,000 times 0.000009. And I want to see if you can write the answer in scientific notation. All right, if you've unpaused the video, what you should have got was 120.6. And by the way, the units there, I won't get too much into this, but the units would be Newton kilograms, like Newtons times kilograms, because we times the two numbers, we times the two units as well. More on that later. Now, if you write this in scientific notation, again, you might want to pause the video and try it yourself. The correct answer is going to be 1.206 times 10 to the second Newton kilograms. Okay, and the second is there because we bumped the decimal place by 2 spaces, 1, 2. And here's another quick question. How many significant figures do we have right here? The answer is 4. The 1, the 2, the 0, and the 6 are all significant figures. Notice there is a 0 in the middle of that string of numbers, and that is okay. You can have zeros in the middle, just the ones before or after don't count when it comes to significant figures. All right, let's see. One thing I'll say before I move along to the next little mini topic is that we won't use ridiculous amounts of scientific notation in this course this year, but you will absolutely see this all the time in physics, in chemistry, in engineering, in astronomy, and it's just an unavoidable fact. So the sooner you are comfortable with that, the sooner you'll be a happy little engineer. Okay, let's go along now to the topic of slope. Slope is absolutely vital to understand. There was an example in a textbook of a ladder resting against a wall, and I like good little physical examples like that. I'm going to go straight for the more kind of like mathy example. I'm going to try to actually use the grid paper that we have here on the screen. I'll see if I can try to match to that. There we go. And we'll go right here. And in some ways, this is easier than a whiteboard. And let's just call every unit can just count as a 1. I am going to mark 2 locations. I can put one right here. And we'll call this location 1. And I'll put another one right over here. And this will be location 2, not surprisingly. Now we're going to label x1, y1 and x2, y2. Okay, the subscript just makes you aware that it's linked back to point 1 or point 2. Okay, x, y, you know how that works. And you know what? I should have labeled my axes because all good. mathematicians label their axes. Now, just off to the side, only because my diagram's a little cluttered and I don't want to make it too busy. X1, oh my goodness me. X1, Y1, in this case is 2 and 2. And X2, Y2, it looks like 1, 2, 3, 4, wait, 4, 6, 8, looks like 9 and 5. Okay. And then we could draw a line connecting those two. Now I could either do a line that sort of goes there and stops there, or of course I could extend it in both directions. The arrows, by the way, on the end of the line, give you a signal that the line could extend off to infinity. It doesn't have a defined stopping point. And that's important. When a line is only between two places and no further, it's called a line segment. And this is more like what we call a ray, extending off. So what is the slope of this? Okay, so the formula is in the textbook. The formula is the letter M. And if you want to know what M stands for, why we use M, it actually comes from a word which I believe is Latin, modulus. There you go. The M is for modulus. And there's actually some engineering quantities that are commonly called, even to this day, like modulus of this, modulus of that. Even though it's kind of an antiquated term in a lot of respects, it is still in common usage the world over. And the formula for the modulus or the slope is, now there's two ways we can say it. We can either say that it is y2 minus y1 over x2 minus x1, or delta y over delta x. Now, I am pretty sure that everybody who has passed through middle school math has done the y2 minus y1 over x2 minus x1. I'd like to also know that you've done the delta y and the delta x. Delta just means a measurable change in. That's the best phrase, I think, to describe what that means. Delta, it's a little triangle. It's the capital D in the Greek alphabet. It means measurable change in. 12th graders, for those who are taking calculus, which I think might be all of you. The reason why I say measurable change, you say like, well, why is it measurable? Like, how can something not be measurable? In calculus, there's the idea of a vanishingly small quantity, which is not measurable. It's like infinitely small. And we use a different symbol for that. And you will see that pretty soon, actually, within probably a couple of months for sure. Okay, so delta y means the change in y, okay? The change in y, the measurable change in y. Delta x is the measurable change in x. Now, in this case, if we just fill in those gaps that we had, we just plug in those numbers, and it looks like we had 9 minus 2. Okay, that was the y2 and the y1. And then we had, oh dear, I've messed it up, haven't I? Forgive me. Let's do that again. Y2 minus y1, I'm sorry, that should have been 5 minus 2. And then the x2 minus x1 is the 9 minus 2. And 5 minus 2 is 3. 9 minus 2 is 7. This slope is 3/7, which is not a neat number at all, but it is a rational number nonetheless. 3/7. When a slope, is 0, by the way, it is a flat horizontal line. When a slope is 1, it is a perfect 45-degree line because you go up as often as you go across. When a slope is undefined, it is pure vertical. That was kind of bonus material right there. Now, the other thing I'd like you to be able to do, the ideal thing would be to actually describe this with an equation. And the equation format, the standard form for linear equations, is y equals mx plus b. The m is that modulus, is that rise over run. Okay, delta y over delta x. So because we've already found that, we can already now say y equals, and then we just fill it in, y equals 3/7 x plus b. And the y and the x are variables. They stay as variables. But the b is another constant that we have to work out. Whenever there are constants, there are variables. Variables we don't want to put in numbers. We don't want to replace them with numbers, but a constant is just a fixed number, which will remain fixed. The way that we get at solving our b is we pick either of those 2 points, the 1 or the 2, whichever one seems easiest to you. I'd say that the point number 1 is a little easier. And we drop those numbers in to the x and the y. And because they were right here, because they were 2 and 2, those are the numbers that I put in. Sorry, I'm just going to keep all my colors. I'm going to go crazy with colors, it looks like. That's the 2 and the 2 that I'm popping in right there. And then we do the math. And maybe I need to just go to black at this point. We do the math and we get 2 equals 6/7 plus b is b. And then we would subtract 6/7 from that. What will we have? Help me out. 14 over 7, 14 minus 6, we have 8/7 equals b. Okay, when we subtract the 6/7 from both sides. So our overall equation, I'll write it up here, y equals, let me try writing that 3 again. Y equals 3/7 x plus 8/7. Not pretty, but I believe it is correct. And the 8/7, by the way, refers to right here. It refers to where the line crosses over the y-axis. The 3/7 is how steep it is, and the 8/7 is the y-intercept, which means my diagram is just slightly inaccurate because mine should be crossing over a little higher than 1, which is 7/7, but it's a little below. So, okay, in the assignment this week, you should find out that those who take the basic assignment in 9th and 10th grade, you won't even have to go to this level of analysis because you're going to do plenty of this later on. 11th and 12th grade, you do need to do this level of analysis, and I know that you will do just fine. Okay, we're doing pretty well. We're up to about a little more than half an hour for this video, and I think we're through the most challenging parts. So take a breath, take a break. If you need to pause the video and come back, get a glass of water, you should do that. I'm going to do the same. I have a LaCroix right here. Hold on. All right. Rearranging equations. This is just simple algebraic skills. And this is just a matter of practice. You will get better at this as you go. I'm going to use the one that is in the book because it's a good example. We have I equals BH cubed over 12 or on 12. This is the formula, by the way, for the second moment of area of the cross section of a rectangular beam. You like that? The second moment of area of the cross section of a rectangular beam. Yeah, that's what that is. I don't know if we're going to get to that this year, but yeah, maybe one day. So what we say is, what if we wanted to make B into the subject? And we got to take it bit by bit. First of all, we would multiply both sides by 12. I am not going to show the little notes, little working out for that, because this is not a middle school class anymore. But we would multiply both sides by 12. And I'm just going to show it like this. This is all the level of working you need for high school. Okay, you do need to show the working, but you don't need to show like the divided by 12 on both sides first. That's a waste of time by now. And then to clear away to get the B by itself as the subject, is what we call that, the subject of the equation, we would divide by the h cubed. And you don't have to worry about the fact that it's an h cubed. It's just a thing. H cubed is a thing by itself. It's multiplied onto the B, so we can get rid of it by dividing. So on our next line, we have that, okay, which is obviously what is in the book as well. Now, a slightly more tricky example was the other one in the book. We had the desire to solve for the h. The h stands for height, by the way. The b stands for base. It's referring, as I said, to a rectangular cross section. Imagine you slice through a beam and you have the height and the base of that beam as you're looking at it, at its cross section. So by the same token, if I start us off like that again, but now I want the h to be isolated, to be the subject of the equation, I'm still going to start by multiplying by 12. And by the way, it's kind of hard to put into words just how to know what to do next. It very much comes with practice. But the way that I typically describe it to people is you're trying to start with the stuff that is farthest away from whatever it is you're trying to isolate. You kind of like start with the outer layers of the onion, and then you like peel it layer by layer to get into it. You can't do it the other way around. That's why the 12 is considered to be like further away from the h than the b is, or than the cubed is. So we're getting like more and more intimate as we cut into that onion. Weird analogies, huh? Okay, we're going to divide by b this time. So 12i divided by b. Still have an h cubed, and we don't want h cubed, we want h. And the only way to like cancel out, as it were, or to get rid of a cube is to perform a cube root. Just like you can do a square root, you can do a cube root. You can also do a fourth or a fifth root or a billionth root. And the cube root is the square root symbol with a little 3. If you don't put a number in front of a square root symbol, it's the square root. If you do put a number, it's a different root, cube root in this case. And notice as well, when I draw my root symbol, my radical symbol, I put this little tag on the end. I was taught to do that by my math teacher. It just helps show with finality that here's where the root like banner stops, and everything under that line is part of the square root. My math teacher's name was Mr. Mitchell. He taught me everything I know, and I'm deeply indebted to him for teaching me little things like that along the way. There it is. H is the subject. Let me give you one more example that just wasn't in the book. Again, it's great if you get into the practice of pausing the video and seeing if you can do this yourself. See if you can isolate, let's say, S. Can you isolate S in this equation? 0.2S. Pause the video. And then you can restart the video. And here we go. What's farthest away from the S? Well, it's the 12t. So we are going to subtract 12t from both sides. What's the farthest thing away from the S? Well, there's really only one thing left. It's the negative 0.2, and take it all at once. Don't take the negative and the 0.2, just grab it all at once. And because it's multiplied into the S, you do the opposite. You divide by negative 0.2. And don't try to think too much in advance, like why that is or how difficult that is or how weird that feels. Just grab it and divide by it. And then you can work out the simplifications in the next steps. So that's the isolation of that. Like, and now if you wanted to, you could go more simplified. You could say, well, let's multiply. And here I will actually show the working here. What if we took the whole numerator and the whole denominator and we multiplied them by 5? And you might say, okay, well, what if we did that? We could have 5y minus 60t over negative 1. See that? You like that? And then you could also say, well, why don't we also multiply top and bottom by negative 1 each? And yes, I could have done that. I could have multiplied by negative 5 to begin with. That's absolutely correct. Some of you are thinking that. You're absolutely right. And that would give us a final answer of negative 5y plus 60t. Make sure you use that distributive property, put the negative onto both of those two terms. And that's a much more nicely simplified answer. Okay, that is where I will leave that. Let's keep on going. Sigma notation. Sigma notation is pretty cool. In fact, there are two ways in which you can use sigma. And they don't really say that clearly in the textbook, but the two ways in which you use sigma are both very, very much related. One is just a little more rigorous than the other. First of all, you can use sigma. Let me write that, by the way, for you, sigma, and it's done like this. This is capital S in Greek. uppercase S. And I do recommend putting those little serifs on the top and bottom. And you have to make it sharp as well, by the way. Just like with the letter Z, you make it sharp so it doesn't look like a 2. You have to make the sigma sharp. Okay, sigma always means sum, like addition. Okay, whenever you see it. And the two ways it can be used, one is sort of a loose way. Like I can say statics is all about when the sum of all forces equals 0. Okay, that is a very loose way, but it expresses the idea perfectly. It shows me that the Jenga tower, the sum of all forces, internal and external, was all equal to 0. And that's why it's a statics problem. You also see this usage, in fact, over the page on page 24. The author says, he puts that inside of a triangle. I can't stand that. I think he should have at least put, wait, what should he have put? Like sum of all angles equals 180? I don't know. I didn't like that, but it just shows you can use it in a very vague kind of way. And then the more specific way that you can use it is how he gets into it in the textbook. Now I'm just gonna, oh, apparently you can't delete that. Hold on. I think I can. If I, believe in myself. There we go. All right. The other way is to show what's called a series, a mathematical series. I think I'll just walk through his example in the book so that you've got it doubly reinforced. So if you want to find the total of P, and by the way, P is often used for forces. P can be used for forces, probably even more often than F in some textbooks. So if you want to find the total P, let's say you had 4 forces you want to add. Force 1, force 2, I don't know why 3 is so hard. Force 3 and force 4. So you can collapse that down by showing sigma P, but you can't just do that. That would be kind of the vague way of doing it, like the concept of adding together all the P's, which is fine. We know what you mean. But if you want to get a little more precise, you actually need to look for the pattern of what's happening. You actually need to say, you know what? There are 4 things here. And we're going to say that the letter N is the number of things, okay, that might exist. In this case, there are 4 of them. And we're also going to use another letter, the little letter I. And this is kind of like it's like a little counting variable. For those who do computer programming, which most of you have done some at some point, we actually often still use I for a little counting variable, like a little disposable variable that's used to like count off, from 1 to 100 or something. And we do it like this. We say, sorry, I'm just filling that in there. We put that little counting variable as a subscript. And then over here, we say, count from I equals 1. Oh, I'm sorry, they just put the N there. So this is more general right now. Put from I equals 1 up to the number N. So this is saying, actually, I'm sorry, this one is more general. This is saying not just when there are 4 things, but when there are any number N things. Any number of things, you can find the total by counting from P1, okay? So we start here, you start at this bottom one, you start at P1, and then you keep counting until you get to Pn, however many N things there are. For our very specific case, okay, for this one here, you would start counting at 1 and you would stop at 4, okay? This is simply a collapsed down version of that. And this might seem unnecessarily clunky to you, but once you get used to it, it's really helpful because we're often in engineering counting up a bunch of things, like lists of things, and then maybe we're dividing them. Like, you know, when you take an average of something, when you take an average of a series of numbers, you add up all those numbers and you divide by them. I could even write that. Let me try to do this off the top of my head. An average of anything is just the sum of all those numbers, starting with the first and ending with the nth, and then dividing, that's division right there, dividing by n, because that's the number of objects, okay? This right here is what seems like an extraordinarily complicated way to say how to take an average. But to an engineer or scientist or a mathematician, that makes perfect sense. Okay, once again, I'll talk you through that. This says add up. That's what the sigma means. So add up all of the numbers, those are the x's, x subscribe, starting with the first one and ending with the nth one. If n equals 100, then you count all the way up to the 100th one. And then you divide by n, which, you know, if you have 100 things, n equals 100. That is a formula which will always guide you through taking an average. And it's so foolproof that you could give that to a computer and it wouldn't matter if there were 50 things, 51 things, 1,000 things. It would always be able to follow that process and come out with an answer. That's why it's so powerful. Okay. All right, we have one more brief topic. We're going to do this in time. This will be great. The last one we're going to do today, we're not going to actually go all the way through to right angle trigonometry, which is what's on page sort of 26, 27. We'll leave that for the next video. We're just going to briefly mention some geometry highlights, and then we'll get you out of here. And as I say, this should be probably the longest video in the entire series for the next 2 months. Now, when I say basic geometry, I mean basic geometry. I want to guarantee that you guys know that, look at that, I'll just clean that up for me, that the sum of the angles, there's my sigma inside a triangle, equal 180. We've got one there, another one there, another one there. And by the way, we have a side, and another side. That's good geometry drawing right there. Using those 3 different symbols for 3 different angles tells the reader that they're not all necessarily the same, or rather that they are in fact different. And then you can see that those little side markings also say 3 different sides. Now, does anyone know what we call it? We have a triangle with 3 different sides. I can't hear you. It's a scalene triangle. I can't hear you because I'm recording this in Mr. Elka's room right now, but it's a scalene triangle. Another little quick fact is that all quadrilaterals, no matter how weird they are, look at that weird one, they always add up to what? 360. Yeah, there's no fooling you. Now, in this case, I can't do those matching opposite like I did. There's just no way to do it because you don't have opposite sides for quadrilaterals. So I just put them anywhere. But that's the sum of all those angles, as I say, is 360. And, you know, that's just the kind of thing that comes up all the time. Now, let's quickly mention radians. Radians were mentioned in the textbook, and this is the one. This is the one topic that I think middle school's recent graduates will have no clue about whatsoever. Okay, you typically don't get much of this until maybe like, well, let's say 10th grade. And we fortunately don't really have to use them this year, but I want to throw it at you anyway, in case it comes up. Radians are an alternate way, a better way actually, to measure the angle of a circle or part of a circle. So just like for a whole circle, that is 360 degrees. If you measure it in radians, and by the way, that little circle degrees, that is the unit right there, okay? Just like we have pounds, kilograms, inches, the unit in this case is that little circle called degrees. The full circle in a radians measure is 2 pi, like 2 times pi, you know, like 3.1415, etc. And now here's where it gets a little bit weird. The pi is not the unit. Radians either don't have any unit at all. Okay, I'm just going to show like a blank space. That's what that's supposed to be. Or you can write RAD in lowercase letters. Either of those are correct. It is correct to not show any units for a radians measure, or it is correct to write RAD to be absolutely clear. In the middle of the circle, I just didn't put anything. And any mathematician is going to know what I mean there. The circle's angle measure is 2 pi. Now, what radians, the reason why it's so useful, I'm just going to draw my circle again. Whoa, okay, thank you for cleaning that up for me. Computer that I'm talking to. When you have a circle that has a radius of 1, well, let's say centimeters. Let's tack an actual unit onto it. 1 centimeter. And the point is that it's 1. That 2 pi measure, you know, 2 pi is approximately equal to 6.283. Okay, 6.283. By the way, how many sig figs is that? It is 4. And that little ellipsis on the end, ellipsis, ... That's called an ellipsis. That means there's more numbers and we just cut it off. That's 6.283. That is actually the physical measure. Like if you could get a blue piece of string and wrap it around, that blue piece of string actually is 6.283 centimeters long. That's why radians actually make a ton of sense. Radians are linked to the physical measurements of the circle. Okay. If you have a half circle, okay, that's supposed to be a half circle. We know that's 180 degrees. In radians, that would be pi radians. Okay. And it just keeps working like that. It's all proportional. Half of a full circle is half of the full circle is half of the number. I don't know how I'll say that. Half of 360 degrees is 180 degrees. Half of 2 pi is 1 pi. If you have a quarter of a circle, just like that is 90 degrees, that is pi on 2 or pi over 2 radians. Okay. It just works like that. That's all we'll say about it for now. If it comes up again later, we'll take advantage of it, but you will see this in your core math classes. Not so much probably in 9th grade, but more in 10th and 11th and 12th. Okay. And our very last thing we want to go to is the Pythagorean theorem. Pythagorean theorem, I know that you know this, so let me just mention it. Only works with right angle triangles. And it's as simple as this. If you have 2 sides, this is not drawn to scale, of course, and you want to know the length of the other side, you do a squared plus b squared equals c squared. C squared is always the hypotenuse, has to be. So in this case, we'd have 3 squared plus 4 squared equals c squared. 9 plus 16 equals c squared. 25 equals c squared. Take the square root of both sides. And we get c equals 5. Okay. And 3, 4, 5 is what we call a Pythagorean triple. Whenever you get 3 numbers that work perfectly with no decimals or anything, and they form a right angle triangle, that's Pythagorean triple. 3, 4, 5 is one of those. 5, 12, 13 is another one. And then any multiple of those as well also works. Okay, those are all Pythagorean triples. Cool. We're going to wrap this up. We're almost at 55 minutes right now. So don't worry too much as a 9th or 10th grader. I just covered about several weeks, maybe even several months of different math topics in 55 minutes. You are reading the first year college textbook. So well done. The main point is that when you open up that basic assignment, you should be able to do that pretty well. If you can do those questions, that's the level of depth that I need if you're in 9th or 10th grade. And you can probably answer over half of those questions right now after watching this video and reading the textbook. So that's it. We'll pick up with some more right angle trigonometry in the second video, and then some units as well. Thank you all for watching. We will see you later. Goodbye.